Okay, so let's go ahead and get started. Does anybody have any questions about the project? No? Okay. If you do and you don't want to talk about it now, you can talk about it after class. We're going to talk about aquatic biomes today. Excuse me. So we'll go ahead and get started with that. Let's see, share screen. Oh, before I start sharing the screen, there are going to be poll questions today, and those are going to be for a grade. They're just simple questions that we've talked about within the last 5 minutes usually, and the way I'll grade them is you get one free. So if there's 4 questions and you answer 3 right, that'll be 100. And that gives room for if you had to step out of the room real quick, somehow weren't paying attention that one time. But anyway, it's just a daily grade, but it's a good way to help make sure you're paying attention. I'm sure it's not a problem in this class, but in some of my other classes, I've noticed when the class is over, some people that didn't have their cameras on didn't leave, and I have a feeling they weren't even there. So it's just a way to help you pay attention. So. There we go. Okay, so aquatic biomes. And if you don't remember, my background is marine biology, so this is more my interest, so I am interested in the other stuff too. But and there's different types of aquatic biomes, and you can see from this simple map, there's a few spots where the water is really, really deep, the abyssal zone. The deepest is over in this area that's 7 miles deep. Then there's the typical ocean. There's lakes, streams, estuaries, which we'll talk about. I spent a lot of time working in estuaries, so that's something else that's near and dear to me. So, but anyway, you'll notice from this map that the aquatic biomes make up a significant percent of the planet. Depending on how you measure it, the water is between 75 and 78% of the Earth's surface. So even though we spend a lot of time talking about land and environmental issues on the land, most of the planet is water. And while we're talking about this is something that's very important for our area. How much of that water is fresh water? And it's not very much. Of all the water available on Earth, 3% is fresh water. So only 3% of the water on the planet is stuff we can drink. Of that 3%, 2% of that is tied up in glaciers and icebergs. We can't drink the glaciers in Antarctica and the Arctic areas, Greenland, Iceland, places like that. So only 1% of the water on the planet is fresh water available to us. And that's something we know well here in the West. By the way, if you're trying to take notes, if I go too fast, let me know. I will put the PDF up later, but if it's hard for me to, in class, if I go too fast, people just say, hey, can you slow down so I can write this down? And that's not happening now, so do it. If I'm going too fast, let me know. Just remember, only 1% of the fresh water on the planet is available to us. And we'll talk about aquifers later, where when you pump water out of the ground, some of those are recharged quickly, but some of them take a very long time, like hundreds of years, and once you're gone. If you are taking notes, remember our guided notes, fill in the blank type notes. Actually, I don't think I put those up yet, did I? I can't remember. If I didn't, I will get them up soon. I apologize, but I think I think I did put them up. Can't remember. Okay, so what percent of the Earth's surface is water? You'll have 30 seconds to answer these, by the way. Okay, and it's, of course, 78%. So, since we're talking about water, let's talk about the aquatic biomes. There's several factors that affect the aquatic biomes. The amount of salt, which is known as salinity. The amount of dissolved oxygen, which is just what it means, with just what it says, the amount of oxygen dissolved in the water. Depth is easy. Turbidity is the cloudiness of the water. So and we'll talk about each of these in a little more detail. It's dissolved oxygen, just remember, fish are breathing underwater, okay? They don't breathe water, they breathe oxygen. And if there's no oxygen in the water, they will suffocate, just like we will if there's no oxygen in the air. So dissolved oxygen is very important to what can live in certain areas of water. So salinity is the amount of salt in the water. It's measured with either a refractometer or a hydrometer. I wish I'd gotten some of those out. I've got one of each here at the house that I use with my aquarium. But a hydrometer basically measures how high something floats, because the saltier water is, the more buoyant it is. And a refractometer measures how water bends, and it looks like a telescope. You hold it up to your eye, but all you're seeing is a grid. And if the saltier the water is, the shadow that you're looking at will change. All the water around here is going to be fresh, so we probably won't use refractometers or hydrometers too much. There's several units that are used, which makes things confusing. I typically use parts per thousand. It's just like percent, except instead of a percent is per 100, parts per thousand is per 1,000. PSU, practical salinity unit, refractive index, and specific gravity. This gets very confusing, especially on if you're used to use. Scientists that I worked with always use parts per thousand. The aquarium community typically uses refractive index, and it just gets kind of confusing if you don't know the conversions and everything. But anyway, specific gravity again is how buoyant it is. So here's some examples. Fresh water, of course, is 0 parts per thousand salt. For 1,000 parts water, there's 0 parts salt. Just an example, because that's where I did a lot of work. Galveston Bay. Bays can change a lot depending on rainfall. If it's raining a lot and the rivers emptying into the bay are putting out a lot of water, the salinity may be down as far as 16 parts per thousand. If it's a drought and you don't have a lot of water coming out and you get most of the water from the ocean, it can be up to 30 parts per thousand. Your typical ocean water is about 35 parts per thousand. Anybody familiar with Laguna Madre? Anybody been to Padre Island? I hear people talking about going to Padre Island for vacations and all. It's in southern Texas. There's a big bay that has very small connections to the ocean. To it, called the Laguna Madre. It's very salty. I've done some work in there, and in places it was salty enough, we had to go down and take core samples. And we're in water about chest deep, and we couldn't get to the bottom to take our core samples. We had to have someone push us down because it was so buoyant. So you would If you wanted to take a core sample, someone would put their hand on your head and push you down to the bottom, and then you could take your core sample, which was just sticking a PVC pipe into the mud and pulling it up, and then you'd stand back up. But if you didn't do that, it was like you were a cork, and there's no way you could get down to the bottom. Then the Great Salt Lake. If you've seen pictures, you can basically sit in the Great Salt Lake. It's so salty. You can sit up like you're in a beach chair and read a newspaper without getting it wet. Very, very salty. And the Dead Sea, of course, is even higher. There are 300 parts per thousand. And it's called dead because fish can't live in it. There are things living in it, brine shrimp, bacteria, algae, things like that that can work with the 300 parts per thousand, but not a whole lot of them. No fish. Okay, next polling question. Freshwater has a salinity of, this should be easy. Okay, so fresh water has a salinity of 0. That's why it's fresh. There's no salt in it. Okay, so most animals can survive at only limited salinities. So the cells of a freshwater animal in saltwater will dehydrate. I don't know how well you can see that, but this is a plant put in salt water, and you can see the cell membrane inside the cell wall shrinks. Let me do this. Maybe you'll be able to see it better now. You see you add salt water, and if you remember osmosis from biology, water tries to go when you've got the cell membrane, if you've got saltier water outside, water will come out and the cell will be dehydrated. So this is why you can't drink salt water. If you drink salt water, your body will get rid of more water to get rid of the salt than you gain from drinking the salt water. And the other way too, the cells of a saltwater organism placed in fresh water will burst. So watch these circled areas. You see the cells just disappear. And what's happening is so much water is going into the cells that the cell membrane bursts, and the stuff that was in the cell just drifts away. Okay, so salinity, there are a few animals, and not very many, but there's a few that can live in fresh and salt water, but they have special adaptations for that. There's some, what are they called? Sheepshead minnows, little small banded minnows, and they can live anywhere from totally fresh water to 100 parts per thousand. Salmon live part of their life in the ocean, part of their life in the rivers. They were born in the rivers, they go back up the rivers to lay their eggs. They have to be able to switch from the fresh to the salt water. And there's others, but for the most part, if you put a clownfish from a coral reef in your freshwater tank with your minnows and your beta, it's going to die. If you put a beta in a saltwater tank, it's going to die. Okay, so dissolved oxygen. Aquatic animals usually need oxygen, especially if you're talking about animals. They have to have oxygen. We shorten this into DO. You hardly ever say dissolved oxygen. You say DO. If it gets too low, they suffocate. And Just because of the physics of liquids, cold water can hold more oxygen, and moving water has a higher DO. So think about this with carbon dioxide in your sodas. That's the way you can remember it. If you keep a soda cold and you drink it, it will stay fizzy for a while, right? Even if you put it in the refrigerator, an hour later you go drink it and it'll still be fizzy. But if you leave that same soda in your car and for an hour while you're inside and you drink it, it's not fizzy anymore, right? That's because liquids can store more gas inside at higher temperatures, at lower temperatures than higher temperatures. So if you're a fisherman and you're using live bait, your bait will stay alive longer when the water's cold in the bucket. In the summertime, when the water gets hot, the fish start to die. Moving water has a higher DO because as it moves, bubbles get dissolved, it gets put into the water, especially with rapids, you get bubbles, and the bubbles let the oxygen dissolve into the water. Okay. So just remember, which holds more oxygen, remember your sodas. Cold sodas stay fizzy longer than hot sodas. Cold water has a higher DO than warm water. Anywhere you have waves and you have a lot of current, your water is going to have more DO. If you have a lake or a pond that's stagnant and not moving very much, it probably will have a lower DO. Okay, turbidity. This is a term just meaning the clarity of the water. Where I grew up near Galveston, the water looked like this. If you stick your head in the water with a mask on, a foot down, the water is pitch black because it's just so cloudy. And it's not because it's not pollution, it's just the waves kicking up the silt in the water. If you take a bucket of this and leave it sitting on the beach for 20 minutes, it'll be perfectly clear. But the waves keep it churned up. You can't see very far. Then on the other hand, in the Caribbean and places like that, the water's crystal clear and you can see 30 feet, maybe even 40, 50 feet through the water. So that's turbidity. And the way you measure that is you take a sample of the water, you shine a light beam through it, and a device measures how much light is absorbed. You can also use something called a Secchi disc, which we have one at school, and I would show it to you, but I didn't go pick it up, and we're not there. It's just a disc that's white and with white and black markings. You lower it into the water until you can't see it anymore. Okay, so what does turbidity mean? Okay, very good. Turbidity is the clarity of the water. Dissolved oxygen is the amount of oxygen. Okay, so in general, we'll divide the aquatic biomes into two types, freshwater and saltwater. Freshwater, obviously, is the rivers and streams, lakes and ponds. Saltwater is the ocean, the estuaries, and the seashores, or the tidal areas. And you should be pretty familiar with those except for maybe estuaries. And I'm not sure if you've heard that term before, especially living in New Mexico, but we'll talk about it. Okay, couple of new words. Limnology is the study of freshwater and its ecosystems. The study of freshwater ecosystems can be divided into two types, lentic and lotic. Lentic is standing water, lakes, ponds, things like that, little or no current. Lotic is flowing water. And in a way you can remember that, lotic, low flow. Low, loat rhymes with flow. Lentic, to me, you could say a round pond looks like a lens, maybe, or just the one that's not flowing is standing. However, I usually like to make up mnemonic devices to remember things like that. So limnology is the study of fresh water, lentic standing water, lotic flowing water. Okay, so the definition of fresh water, little or no salt, has a very low salinity. Depending on the areas, you might get a few parts per thousand. But in general, if you're saying it's fresh water, there's very, very little or no salt. Lentic, again, rivers, and that's backwards. That's weird. Okay, hold on just a second. Yeah, these two are backwards. So use these words, not the other ones. Lentic is standing, lotic is flowing. Not sure how that happened. I will definitely fix that. Okay, so streams. The faster a stream flows, the greater the amount of dissolved oxygen in it. Rapids are going to have very high dissolved oxygen. So mountain streams that are flowing and having waterfalls and all of that kind of thing are going to have a very high dissolved oxygen. White water, by definition, is water with lots of little bubbles in it, and that's going to cause a very high dissolved oxygen. Okay, just remember, the faster the water, the higher the dissolved. Okay. Fish that are living in streams are adapted to fast-moving water. Obviously, if they weren't adapted to fast-moving water, they'd end up in the ocean instead of the stream, right? They have to be able to swim against the current. And there's lots of organisms that have, if you live in the streams, in the rivers, you have to deal with current. If you didn't, eventually you would end up, if you've ever spent any time in a river, done any canoeing or anything, if you don't fight the current, you're going to end up downstream. And over generations, any organisms that can't fight the current are basically going to end up in the ocean. So, freshwater clams. Freshwater clams, this particular type has an amazing adaptation to keep from ending up in the ocean. So basically, the larvae, the baby clams, have these spikes on them, and they latch themselves on to the gills of a fish. Because a baby clam can't swim, but fish can. So they latch themselves onto the gills. They actually drink some blood from the gills. There's lots of blood in the gills. And when they get big enough that they won't get washed downstream, they drop off and grow up into a clam, where they do their regular filter feeding just like any other clam. So how do the baby clams that can't swim very well get attached to the gills of a fish? Okay, first of all, next polling question. What happens to the dissolved oxygen as the speed of the water increases? Okay, so The faster the water, as the speed increases, the dissolved oxygen increases. Just think about the bubbles getting mixed in the water. Okay, so these clams have lures, amazing lures. They have a part of the mantle of this clam that looks like an animal, and they wiggle it. Look at this one, especially. There's an eye spot, fins, a tail. They wiggle this, and the fish comes down to eat it. And when the fish attacks, the clam squirts out all the babies right into the mouth of the fish. Look at this one. And this is what the gill filament looks like with the clam stuck onto it. This one looks a lot like an insect larva. There are insect larvae that look a lot like this. These look like worms. This one actually looks kind of like a crawfish when you see them move it. And of course, little fish again. Let's see if I can get this to work. Okay, so watch this one. Look at this one. And look at the fish that lives in the stream with it. It looks almost exactly like that fish. And it wiggles them in such a way to make it look like a tasty meal. This one looks a lot like these insect larvae. Here's a quick video talking about them.
In the streams of Missouri lives the Lampsilus mussel, a simple animal with an extraordinary life cycle. To reach adulthood, its young must spend part of their lives inside a fish, the largemouth bass. To get there, the mussels must make physical contact, a difficult task, as mussels don't swim. But the bass has a weakness. It's a voracious predator of small fish, particularly darters. Even the slightest wriggle of a darter's tail will attract bass. Believe it or not, the fish on the mussel is an imitation, a perfect replica that will lure bass within striking range. The mussel can somehow sense approaching fish and wriggles its lure faster to entice them. If it gets the twitching just right, the remarkable likeness should do the rest. On impact, the mussel squirts its young into the bass's mouth. These snap shut on the gills, like spring-loaded traps. Here they stay, drawing blood from the fish, until several weeks later they drop off as tiny, fully formed mussels. Also a favorite prey of the bass are these striped shiners, and some mussels mimic them. Considering mussels are blind and have never seen a shiner, the likeness is incredible. The eyes, fins, and even the stripe look just right, yet the mussel knows nothing of its own appearance. These lures have evolved because bass more often attack mussels that look like fish, so fishy-looking mussels leave more descendants. After millions of years of blind evolution, this process of selection has turned mussel flesh into a lifelike lure. It takes a good imitation to fool a bass in clear water, and some of them are incredible. This darter mimic even has a mouth which gulps. This mussel is the same species, but its curious leopard print design may not find a taker, and its genes will go no further. This lure looks pretty good, but the bass is unconvinced and turns it down. Mussel lures are constantly improving, but fish are getting ever better at recognizing fakes. It's another arms race, and it's still creating diversity in the streams of Missouri to this day.
Okay, so that's pretty amazing to me. And remember, the whole point of that is because the fish, the clams, if they just release their babies into the water like most bivalves do, they would drift downstream, and each generation would be farther downstream, and eventually they would be in the ocean, which is a bad place for a freshwater mussel. So they've got to have some way to go upstream to spread their range and to just stay where they are. And fish can swim, and they can go wherever they want to in the current. Okay, so some characteristics of flowing fresh water. Water moves slower in a river. Okay, so we're talking about rivers now versus streams. Rivers move slower. The debris settles at the bottom. Because of this, they tend to have more nutrients and less dissolved oxygen. Think about a stream flows down from the mountains. It starts to level off and it becomes a river. The river is in flatter areas, so the water is not going to be moving as fast. And all the nutrients and sediment that were carried by the streams are in the river now, and as the water slows down, it can't carry as much sediment. The slower the water, the less, just common sense, if the water's not moving very fast, it can't carry as much sand. And the sand and the dirt starts to fall out. So you have more nutrients carried down from the streams in the higher elevation, lower oxygen because it's not moving as fast and not getting stirred up as fast. Usually rivers still have enough oxygen to support fish, but it's not going to be near as high as it was in the streams. And you know what rivers are. Okay, so we're about to go into the lentic, the stiller waters, so we'll go ahead and stop here. We'll continue on tomorrow with the ponds and lakes, and then go start talking about the marine biomes. Okay, so if you don't have any questions about the project or anything you want to talk about, you're welcome to go. If you do have anything, stick around and